Greedy ladies and gentlemen, I'm glad to have the opportunity to present my paper, and I'm reporting about the electrochemical senses of ferrate. Six factors influence synthesis and currently research triggers. My paper is a review, and in my introduction, I will present my content in four aspects. In my introduction, as we know, ferrite has six value state of iron, which has relatively strong oxidating property and can be used as water treatment, character, and bacterial electromaterials. It's a kind of green material. There was three preparation method and electrochemical method as a reaction condition mild method. This is by the scientific community widely attention. Next, I will discuss the researches from the scientist study respectively to the electrochemical senses of ferrite, the effect of varied process factor on the senses of the researchers. The first factor is the anode materials. In the context of the electrochemical ferrite senses, the anode plays a pivotal role as both an electroacceptor and a source of the iron. Concerning an anode materials, a device range of the iron containing electrodes has been widely employed, subsequently giving rise to the application of carried electrode. These iron-containing electrodes in compact, varied forms of iron, including pure iron, iron alloy such as carbon steel, silicon iron, and iron compounds, contingent on their composition. Structure varies also in compressed configurations like iron block, iron wire mesh, iron ponder, and sponge iron. Concurrently, carried electrode as an emerging range of study has found utility in the electrochemical senses of ferrite, employing directly electrosenses of iron loading, changing the compositions of the electromaterial and increased their surface area can also be enhanced the efficiency of ferrite generation. Inexpensive and highly oxidation electrode has significantly research potential. However, the current reaction mechanism involves both the free radical and the atom oxidation synthesis pathway. If the pollution are directly degraded though online electrolysis, the generation of ferrite occurred after the complete degradation of pollution. The second factor is electrocomposition. The electrochemical synthesis of ferrite is typically carried out under strong alkaline condition, with the main electrolytic solution being sodium hydroxide, and other alkaline hydrogens can be used. The electropolymers carried is pH. Under acid and neutral electrode condition, ferrite rapidly oxidates with water to produce the ferric and oxygen, which can be directly employed for pollution degradation. It has been observed that the degradation of ferrite occurred at a first-order rate. To synthesize the ferrite, the electrolyte is typically maintained under strongly alkaline condition. A mixed electrode exhibits advantage in the synthesis reaction. However, excessively high sodium hydroxide concentration may result in electron preservation. And the percent of the ferrite adherent to the anode could impact the ongoing oxidation of the iron atom. The second factor is additive in electrolyte. Different additive in electrolyte has varied mechanisms of influence, closely related to the electronegativity of additive. One tapped of the electron ion absorbed around ferric, reducing the catalytic decomposition of the ferrite by ferric. Other tapped of the electrolyte ion can trigger in the generation of free radical, promoting higher ferrite production. So, mining factor can also facilitate the production of the high radical in alkaline condition. However, under acid condition, it reacts rapidly with electro denoting group. There is yet a type of the electrolytic ion that does not react with hydroxide radical and remaining inert during the electro-oxidation process. The fourth factor is the reaction temperature. The influence of the reaction temperatures on the electrochemical synthesis of ferrite can be summarized in two main aspects. Firstly, raising the temperature can enhance the reaction activity, elevate electron surface pathway, and consequently improve the reaction rate. Secondly, elevate temperature can also lead to side reaction involving oxygen, accelerate the decomposition of the ferrite. The first factor is the coolant density. The impact of the coolant density is not only related to the magnitude of coolant density, but also to a way the coolant is operated. Increasing coolant density permits the generation of ferrite, but at high coolant density, more oxygen is produced at the electrode. Meanwhile, the increase in temperature due to coolant density handing of the electrode accelerates the decomposition of ferrite. Changing the method of the coolant application can reduce the likelihood of electrode pathways and improve coolant efficiency. The sixth factor is the membrane, ion exchange membrane, in the electrochemical synthesis process. To prevent the diffusion of ferrite, generate at the anode to the canister for reduction. Membrane is introduced between the anode and the canister of the reaction. This membrane not only need to be handle the diffusion of ferrate, but also must permit the fluent of electrocurrent and the exchange of the necessary ion. The primary function of the member is to facilitate to the migrate and the inhibition of the speech ion. For example, anion exchange membrane allows the free migrate of the hydro ion, while a cation exchange membrane can impede the migrate of ferrate ability concurrently, indicating high potential. Furthermore, ensuring the flow of current is also a crucial factor to consider. The last factor is the reaction type. Best electrode cells are commonly used for the electrochemical synthesis of ferrate, and the configuration was about 4 times more effective in producing iron 6 than a single casenode or single anode step. A research utilized a quinlandro electrode cell for their experience, achieving a ferrate salt concentrations of about 14.8 millimolar per liter after a reaction time of the 6 hours. The state of the electrode cell was depicted in Figure 6. The choice of the reactor can be selected and designed based on actual needs. The paper critical analysis the various factors affecting the synthesis of ferrate by the electrochemical method, regard the choice of the electrode using high surface area anode material or Peru carrier electrodes as anode materials exhibit superval electrochemical performance. The composition of the electrode significantly affects the pH environmental of the electrochemical reaction. Achieving efficiency reactor rate required optimizing the diffusion of a reactor within an appropriate pH range. The choice of the electrode can have varied impact on the reaction outcome, and the underlying mechanism can differ depending on the electrode needs. Maintaining an appropriate temperature is benefit for the electrochemical reaction, as it enhances reactivity, but excessively high temperature can lead to the decomposition of synthesized ferrate. The impact of current descending is notable mainly at a low value, while high current densities can lead to electropreservation. Techniques such as electrocurrent and parcel-based method can increase the ferrate yield under certain conditions. Various types of ion exchange members include annual junction and bipolar members can serve as separator in the electrochemical senses of ferrate. The focus is on achieving high ion fluids and coolant density. Different types of electrolytic sense, including conversation, double case single angle anode, and quilindial cells can be used as a reaction device based on spatial needs. The paper also introduced the direct senses of ferrate using insert electrode. For example, BDD is mixed light in the director articulate of iron in the solution to sense the ferrate and operate it for pollution degradation. Furthermore, the paper mentioned plasma technology (SPP), which offered an efficiency sensed approach for electrochemical ferrate production. There have several future perspectives shown in my paper. If you have some interesting, you can find it in it. And that's all. Thank you.